Okay, well, good morning, everyone. Can you hear me?
Yep.
Great, okay. Good to see everybody. Pleasure to be here. Thank you for the invite and congratulations to the Unified Water Study for the South Shore Estuary Reserve. That's really wonderful news, so congratulations. Okay. All right, well, I think, we all know where we stand. I gotta get rid of that guy though, huh? You can see that there? Let's see, if I can hide that.
Oh, I'm sorry, I'm recording.
That's all good. Okay. Well, we know the unique situation we live in here in Long Island.
I'm sorry,
What? It's recording, I know that.
It is recording?
I just
Okay.
hit the
The
button,
hide button?
so,
Okay,
yeah,
thank
yeah,
you.
yeah.
Sorry.
All good, all good. All right. So the unique situation we are in here on Long Island, every drop of water that falls on land is doubly important. It's our drinking water source, and there's only one option there. And then beyond that, we know that what we're not extracting to drink is discharging into surface waters, and that's going to affect what's happening in those surface waters. In fact, it was almost, more than 50 years ago, scientists declared that nitrogen is the limiting element in New York waters. And that means that as soon as you add a little bit of nitrogen, the ecosystem is going to change a lot. And we know what's happened with nitrogen over time. The levels keep going up. And we know there's great diversity in that nitrogen level. So you can see the average here is about 3.8 milligrams per liter of nitrogen in drinking water across Suffolk County. But that varies a lot. There's some areas that are low, but other areas that are quite high and well above that. And I'm going to focus on marine waters momentarily, but just to talk about drinking water just for a moment. This figure you're looking at here is a study out of Duke University that looked at all the drinking water supplies for the entire nation. So that first bar you're looking at, the unit, if you can't see it, is 200 million. And what it's telling you is that 200 million people in the United States have drinking water with less than 1 milligram of nitrate per liter. And then what you can see for the average of Suffolk County is that we're way off in the tail, in the upper 5% of nitrate levels in drinking water. And that's something to be concerned about. In Stony Brook, we have a medical school, and I speak with the doctors and epidemiologists there, grown relationships with them through the years, and talking about emerging evidence. And some of that evidence and research that's coming out of Europe, but also out of the National Institutes of Health, is the potential health risk with high levels of nitrate in our drinking water. The standard federally is 10 milligrams per liter set by the EPA for something called blue baby syndrome. It's very, very rare. But these new epidemiological studies are showing that high nitrate has been linked epidemiologically with incidences of cancer and even birth defects. And the concerning aspect there is that it's not at 10 milligrams per liter, but it's as low as 2, maybe up to 5 or 6. But in that zone we're in right now. So from a public health perspective, there's motivation to get the nitrogen levels in our drinking water as low as possible. But moving on to the marine world, we know where that nitrogen's coming from. The studies have been done over and over again for both Nassau County and Suffolk County. And maybe it shouldn't have been any surprise given the density of people in Long Island. The nitrogen's coming from wastewater, and in Suffolk County, by and large, is from on-site wastewater. And as you can see here, when that wastewater gets into a groundwater, it discharges into surface water and can exact an effect on marine ecosystems. This is a map that it's in draft phase. We're almost done, almost done. I thought I'd have the final version, but we're not quite done. The reason it's not quite done is couldn't be more up-to-date data. This is a map of water quality impairments observed on Long Island since April of this year. And what you can see is a widespread occurrence of, in the blue, what we call hypoxic zones, also known as dead zones, low oxygen zones. And all the other colors are what we call harmful algal blooms. Although I should say there's some fish and turtle kills in there also. But if you look at that map and just stand back, there's a few things that should jump right out at you right away. Particularly if you know the areas that are sewered on Long Island and the areas that are not. And the fact of the matter is, when you look at Nassau County and Western Suffolk on the South Shore, where areas are sewered, you don't see a lot of water quality impairments. But when you get to these areas that are unsewered and you've got those septic systems discharging into surface waters, there is an abundance of harmful algal blooms, which are all the other colors, and these dead zones. And it's probably not by coincidence there. And I'm going to review some of these events right now. So, as I said, many of these are harmful algal blooms, both marine and fresh water. Some are the type that are harmful to humans because they make biotoxins. Others are the types that are harmful to marine ecosystems. They call them ecosystem disruptive blooms because they can cause things like fish kills or cause mortality in shellfish. So I'm going to start reviewing what we saw in 2023. And I'm going to start with actually the harmful algal bloom that I find the most concerning of them all. This is Alexandrium. It makes saxitoxin. Saxitoxin is a neurotoxin. It's 1,000 times more potent than cyanide. And it causes something known as paralytic shellfish poisoning. You're looking at the molecule right there. I won't go through the details, but if you're close enough, what you can see is this is a nitrogen-rich compound, right? And the studies have been done over and over again. Give the organism more nitrogen, it can make more of a toxin. And that's why nitrogen actually plays a dual role in these blooms. Not only does it promote the events, but it promotes the toxin synthesis by the organism. And in places like Alaska, this can be a lethal outcome. In fact, the first incident of PSP and that was known was 100 people who died in Alaska from eating poisoned mussels. So before this year, we actually have had, as you can see, 7 different locations that have been closed to shellfishing by the DEC because of high levels of saxitoxin in shellfish. Now, the interesting thing is we had never seen this anywhere in New York before 2006. I was there when it first happened, and we all thought it was a mistake. Oh, these are mussels coming from Maine. But in fact, that wasn't the case. And you can see many places have been closed to shellfishing in the subsequent 15 years. But 2023 was an unusual year, actually record-setting with regards to the number of places that were closed to shellfishing because of this organism and its toxin. And you can see areas on the east end, so places like, it started with on the east end in Terry Creek, and the adjacent Meeting House Creek, and then expanded to most of Flanders Bay, which is the eastern extent of the estuary. Further out in the estuary, there was a closure in a place called Jockey Creek and Town Creek. And then on the South Shore, the whole eastern extent of Shinnecock Bay was closed as well. And I should say of these, the closure in Flanders was a first time ever, and the widest spread we've seen in Flanders Bay. And then another first time ever this is in Mauritius Bay, and actually the eastern extent of Mauritius Bay, a closure there as well due to PSP. So that's 5 different closures. We've never had that many in a given year. And just making the nitrogen link as clear as possible. This is an experiment we had done last year when we collected water from Sag Harbor that had really low levels of the organism. You can see almost undetectable. And then just in an experiment, let's collect the seawater and let's see what the organism does on its own. We'll give it nothing or control. We'll enrich it with nitrogen or phosphorus or nitrogen and phosphorus together and see what happens. And just in a matter of days, you could see the organism increased relative to the control by 2.5-fold just by adding nitrogen, right? And this isn't a toxin, this is just the organism, but it just shows the strong effect. And this is consistent with another study we had published years prior, not only showing the link with nitrogen, but showing the link with wastewater-derived nitrogen, specifically in the Northport Bay region. Now, the sister bloom to this is known as, to Alexandrium, is something known as dinophysis. Dinophysis is also a dinoflagellate. It makes something called oxidaic acid, which is also a toxin, can lead to shellfish bed closures. It has been something that we never saw really on Long Island. It has now become common. We see it every single year. And an interesting thing happened many years ago when we first started studying this. I love presenting locally, but I also love presenting globally. I'm going to Japan in a couple of weeks to present to an international conference. And I think the conference I was at was in Korea, maybe, in 2012, right? During Hurricane Sandy. And we were presenting on our research on dinophysis there. And, we were presenting a poster, my student was, and we had a bunch of scientists come and say, oh, your numbers are wrong here, that your densities of dinophysis are too high. And we said, no, actually, that's the number we recorded. It was 2 million cells per liter. And, not that anyone cares about these things, but, this consensus was, this is by, international, well, that's the highest we've ever seen. And in fact, I've published group papers with other scientists since then where we're comparing these syndromes across the world. And in fact, this was the highest ever seen, 2 million cells per liter. This past spring, we had an incident that really made us take a step back. We saw a bloom specifically in Seatuck Creek region where we had over 100 million Dinophysis cells per liter. And now, oftentimes when you see a high level, or level that high, it's like a blip. It shows up and it's gone. You say, "Ooh, God, that was scary." This went on for a month, where we had millions and millions of cells in this area, just kept persisting. You can see what the water looked like there. And again, thought it would go away, but it started in May, persisted well into June. Then it led to just the second ever DSP closure we've ever had in New York State. And frankly, this is an area we hadn't even known about. I sometimes like to think about that, oh, we've monitored it all, but you showed how many sites there are to look at out there. And so this was when someone tipped us off and said, something looks wrong with this creek. Could you take a look? And sure enough, that's what we saw there. Now, unfortunately, I wish this story would just end with Dinophysis, but there are other harmful algae out there also, diatoms, and I'm going to introduce a new one to you here known as Pseudonychia. Causes amnesic shellfish poisoning. This has been widespread globally. This has been something that had exclusively been on the West Coast. And I have colleagues there who've been saying for many, many years. But it looks like it may be an issue for us as well. Unlike these other organisms, it's what's known as a diatom, which often we associate with healthy ecosystems, and it makes something known as domoic acid. I won't go into the details here, but I will just say that glutamic acid is the most abundant neurotransmitter or excitatory neurotransmitter in your brain. So the reason that domoic acid is a problem, and you don't necessarily need to be an organic chemist to know, the structure of domoic acid looks like glutamic acid. So if you get a high dose of domoic acid, it's binding where your glutamic acid should be binding in your brain, and has bad outcomes for your neurons as a result. It can lead to the death of neurons, essentially. There's a whole host of symptoms that start as gastrointestinal and then become central nervous system issues. And the most famous event of amnesic shellfish poisoning was in Canada in 1987, a place called Prince Edward Island. So for those of you who are mussel enthusiasts, you go to a restaurant, you see on the menu PEI mussels. Well, that PEI is Prince Edward Island. Now, this has only happened once there. This is many, many years ago, but it's a terrible event. Hundreds of people got sick, 3 people died because of the accumulation of domoic acid in the mussels. This map here shows on the, you can see the map shows where domoic acid has been an issue, mainly on the West Coast. And in fact, if I made this map just from a few years prior, you'd see nothing on the East Coast, but you can see it's sort of now bubbling up in the Northeast. And on the bar graph there, you can see there's a significant increase in the incidence over time with regards to these blooms. And on the West Coast, it's been very problematic for marine mammals, specifically sea lions, intoxication and death, because it accumulates up the food chain. Planktivorous fish will eat it, and then it goes up to the sea lions. And the graph you can see there, the increasing incidence of sea lion intoxication associated with this toxin. And so I wish I wasn't reporting, but I'm sorry to report that we detected this in the South Shore Estuary Reserve late this summer. You can see the sites from Nickel Bay all the way through Western Shinnecock Bay. The most intense spot was actually in Seatuck Cove, like that spot before. Now, the organism doesn't necessarily make the toxin, right? There's over 50, I believe, 50 species of Pseudonychia. Some are toxic, some are not. But we used a technique called SPAT, and that stands for Sorptive Passive Toxin Trackers. Put this resin out, it absorbs things in the water, including the toxins. You can extract it and see, well, was the toxin present? We've just looked for 2 days, and this is sort of, I would call, breaking news, but we did find domoic acid in the water. So not only is it the organism present at high levels, but the toxins present as well. And we would have missed this. This organism is super small, but it just so happens I brought into my lab a scientist who worked for the Maine Department of Natural Resources, where they're on the lookout for this because it's a regular occurrence there. And she said, you have Pseudonychia in the water. And we hadn't seen it before. It was so small, we had missed it. So it's probably not new, but we don't know a lot, except for the fact that we saw it come up in late August and was gone by September, but it was there and making toxins. Many unanswered questions. We don't know how long it's been around. We're doing some archive work. We know the toxin is there because we picked it up, and it was at significant levels. It wasn't at the detection limits. We were very easily able to measure it, but we don't know what it means from for example, from a shellfish point of view, or if it was a one-off and where else it might be happening. But it's something on our radar and certainly something to be concerned with. Just going to quickly go through this, but it is worth mentioning for those who aren't familiar with Daisy japonica. This is the red seaweed that is invasive, japonica, because it's from Japan. And we now know that it's spread throughout Great South Bay, and you can actually find it all over South Shore, North Shore, East End. This is our first survey showing it's spread through the South Shore. And we know it can be a human health threat with regards to if you get its overgrowth and it begins to decay, and the overgrowth is what we've seen in Great South Bay at times in the past. And on the right is the decay state, where it had been decaying in a canal in Great South Bay. And when it decays, it can create hydrogen sulfide. Hydrogen sulfide is a toxic gas. And there's been studies that have shown that people can be intoxicated, brought to the emergency room, and it even can cause death at high levels. So it is something to be concerned with when it overgrows. If you just see the seaweed, I just want to emphasize this, so I do get these questions. The living seaweed on its own is perfectly harmless, but it's when it's decaying, and that decaying state is when it can create hydrogen sulfide gas and can be problematic. Beyond the hydrogen sulfide for humans, we also know that in that same decaying state in the water, it releases a red pigment. That's why the water looks red. When we first saw this images like these, we have thought it was a dinoflagellate, which is also red, but it's not. It's the pigment leaching out from the seaweed, and it looks horrific. And turns out it actually is a little horrific because it's toxic to marine life. We were able to show it's toxic and can kill larval fish. Same thing for larval bivalves. I should mention, it was obviously in the Pacific Ocean. It spread through at the end of the 20th century Europe. The first sighting ever anywhere in all of North America was only in 2007. So it's only been affirmed in a few sites. First showing up north of us, but it's I guess you can call it endemic to our waters. And we've shown experimentally, it loves more nitrogen, it loves more carbon dioxide, and it loves getting both of those things together. And we know the carbon dioxide levels in our atmosphere are increasing and in our waters. And we also know actually higher nitrogen can lead to higher levels of CO2 by creating more organic matter that degrades and then turns into CO2. And then finally, we took the tissues of this organism, surveyed all across the South Shore, and did what we call isotope fingerprinting of the nitrogen in the seaweed. This gives you a very clear sign. Essentially, you can tell whether the organism is using fertilizer as its nitrogen source or wastewater. And we got a direct hit for wastewater almost everywhere. And maybe in some cases, it was 75% of the nitrogen coming from wastewater and the other fraction probably coming from fertilizer. Okay, so I won't go through all the details, but we do know that when you add more nitrogen to our waters, I already showed you for Alexandrium, we did the same thing for Dinophysis and for other harmful algal blooms like Microcystis. They grow faster, and in cases of nitrogen-rich toxins like saxitoxin or microcystin, they can make more of those toxins because they're nitrogen-rich compounds. And I'll just mention also that high levels of nitrogen can lead to low levels of oxygen. I just mentioned this before. This image here shows that decaying, when you get a phytoplankton bloom, eventually it's going to decay. That decay, carried out largely by bacteria, robs water of oxygen and produces CO2 at the same time. So that's that CO2 we were referring to before. We have standards by the DEC for oxygen at 3 milligrams per liter. And I would say 10 to 15 years ago, we looked at all our waters, the Suffolk County data set, and it all looked great. The levels of oxygen were high. The problem is we were measuring those during the day. And what we've come to learn now that we have sensors that are logging every minute, every 10 minutes. It's a very strong day-night cycle. And we have something that's called nocturnal hypoxia, low oxygen happening at night, and it's ubiquitous. And you can see most of the locations that we survey across Long Island are experiencing this at night. And I can say this summer, particularly when we had the high heat and lots of rainfall, almost every site that we're measuring across the South Shore was experiencing nocturnal hypoxia. And that's going to change the ecosystem, right? Some organisms don't have a problem with that. You know, bacteria can thrive, but others are going to leave and aren't going to enjoy that whatsoever. Okay, well, I'm going to transition a little bit now and just talk about climate change a bit, because as we think about managing and protecting our natural resources and our aquatic ecosystems, yes, we need to be concerned about nitrogen loading, but we also need to be aware of the fact that climate is changing in parallel. So we need to be mindful of that. And many people like to use the term Anthropocene, which just means we're in an era where the activities of man are overwhelming and dominating the forces of nature. And I don't think anybody would take issue with that. We know what the trends have been with regards to temperature. You can see since 1980, global temperatures are rising very quickly. And there's been other consequences. We all forget, but remember those 3 days in June where the sky was yellow? And that's just another symptom of climate change. And I'm sure you're all aware, but we are in one doozy of a year. So this is a plot here, if you can't see it, of global temperatures during summer. And so you can see everything's on a line. The warmest summers, of course, are some of the more recent ones. But that one point that sticks out, if you can't see in the back, all the way up there, that sticks out way above the line is 2023. So we're in the midst of something very unusual. And honestly, I'll be perfectly honest. Many scientists are stumped, right? There's some things that account for this. For example, we know that in good news, we're reducing things like particulate sulfur and other particulates out of our atmosphere, right? And that's great because those particulates, when you breathe them in, are a very serious lung issue for people. We know that that type of air pollution can actually is responsible for a lot of deaths globally. But those particles actually had reflected back some of the sun's energy. So while we're reducing fossil fuel emissions, that had actually leads to some warming, but only a small amount, like 0.1 degrees. So something's going on, and in a lot of climate models, they account for things like tipping points, but we're not in a normal cycle right now. I can just say that. But the important thing to recognize with global warming is that the temperatures globally, frankly, don't matter, right? Does anyone in this room really care the temperature that it is in, say, Argentina right now? Right? And maybe we do. We don't want bad things to happen to people there. But what's important is what's happening for our ecosystems, and for the South Shore Estuary Reserve is what's happening locally. And what's of interest is that we've actually been experiencing warming during summer at a rate that's 4 times the global average. So not only are the temperatures getting really high, let's say in 2023, but we're in a hot zone. But I want to emphasize this is during summer, right? So I can point to other seasons where it's not warming at that rate, right? So for example, in the spring, our springs are actually no different. And this is the thing about global warming. It's different in space, it's different in time. But if I had to choose a season for our warming to occur, I would not choose summer. Because what summer already represents, as you know, is the thermal maximum, right? So now we're getting a thermal maximum that's increasing. Well, everybody's having that, but at a greater rate. And what that means is marine life and marine processes and aquatic processes are all experiencing something brand new, and that can have consequences. So before I get into just the temperature part, I think everybody at some point this summer, but anyone, raise your hand if you experienced a tropical deluge of rainfall this summer. I know that I did, right? Some unusual rainfall where you walk out and it's not raining, it's just the skies are open and you are getting drenched. And this is a new phenomenon. And I'm just showing here from essentially during the summer, what the temperatures were like, and then some rainfall events as well. And so every time you see a bar that's really sticking up, that's an unusual rainfall event. So that's like more than an inch of rainfall falling all at once. And that's one of those tropical deluges. And And this is part of a pattern that has been going on. This is showing you the change in what NOAA would call very heavy precipitation across the United States. And of course, it's up everywhere. And this is associated with temperature changes. So we're in an area where warmer temperatures, more evaporation, more liquid in the sky, that is more likely to come back down as precipitation. But you can see, since the middle of the 20th century, we're in a zone that has had this happening faster than other places. And that may continue. And that may be associated with the rapid warming we're experiencing. So, don't want to be the bearer of bad news again, but let me just introduce one other thing to be concerned about. And that's something called Vibrio vulnificus, right? And this is important to be aware of on multiple fronts. First thing I want to emphasize that people often use this term Vibrio, and for some good reasons, but every Vibrio is slightly different. Right? And so this is a specific species. It generally has been known to occur in the South in very warm water, and it become an issue like the harmful algal blooms that it can accumulate in shellfish. But this also is a species that can infect wounds. Right now, the likelihood of that happening is dependent on many factors. Your state with regards to your immune system, the type of wound you have, your age. But the bottom fact there is a really scary one, and that is 1 in 5 people infected die if they're infected with this infection in 1 to 2 days. So it's very rapid. Right? So again, extremely rare, and unfortunately something we never had to worry about. But what this is a paper that came out just this year, and there's a grand irony of this paper. I'll just walk it through with you. And what it shows is where Vibrio vulnificus was present in the U.S. over time. And essentially what it shows is that it was present just in the South in the 20th century, and it sort of has creeped up the coastline, with the closest incident being in New Jersey. And then they put together a model and saying, okay, well, if we consider where we're going with increases in temperature, where will Vibrio vulnificus show up? And essentially through their different models, it said, well, if we have lots of CO2 emissions, and if we wait till the end of the century, Vibrio is going to make its way all the way to the Northeast, and including Long Island. Well, they were a little off in their predictions, unfortunately. And those if you didn't know, we had people in New York and Connecticut contract Vibrio, both from flesh exposure and potentially from eating oysters. I will just say that, well, I'll say a few things. One, the oyster issue is, I think, to my mind, hadn't been resolved exactly where the oysters come from. I need to get more information on that. And two, these are the people that died. There are instances of people getting sick, and it's hard to know what was happening there because, of course, no one in the medical community is testing for this. Someone comes in with a flesh wound in an area where we think this is happening. How would a doctor know? Doctors just didn't know. And that's why the CDC put out this alert. It didn't come out until September, but essentially just saying, hey, doctors, this is a new emerging issue. You need to be on the lookout for this. And I'll just say that this showed up following the heat waves we had this summer and following all those tropical deluges. And so, it's now on our radar, and it's something to be certainly on the lookout for and getting more information on. Okay, so warming's an issue. Happening along with that is something we call ocean acidification. By laws of physics, warm water holds less oxygen, and I've already talked to you about dead zones and low oxygen zones. And we have harmful algal blooms happening at once. Sometimes I call these the 4 horsemen of the ocean climate change apocalypse. Warming, harmful algal blooms, acidification, and low oxygen, because these are all happening at once. All marine life is affected to this. And frankly, from a scientific point of view, we know a good bit about how each of these things affects marine life. We know very little about how these things in unison, or even just say in tandem, may be affecting marine life. So it's a really active area of research, and one to be concerned with. And so I just want to turn to, as an example of these multiple stressors, the collapse of the bay scallop fishery on the eastern end of Long Island. If you didn't know, this was one of, I think, 3 federal fisheries disasters declared by this country. because the landings went down 99%, where they had already been down 90%. And that, as you can see, occurred starting in 2019. And, you know, to my knowledge, no one's really excited about this year's harvest necessarily either. But we did do a study of this, and this is sort of gives you a sense of what may have been happening there. You can see the title, warming and hypoxia. So two of these stressors together and how that affects these scallops. So here's the warming rate. And you can see here's some data from the eastern end of Long Island. And you can see warming at more than a degree Celsius in a very short period of time, just 17 years. I will emphasize this is just for July and August. And I'm going to point out a little place here, Napeague Harbor, all the way out in East Hampton. Beautiful place if you've ever been there. Note has the lowest degree of warming. And I'll also note that this is maybe one of the last stands for the bay scallop present. I already told you that as water warms by laws of physics, it holds less oxygen. And I had a student, he's now a professor at the University of Maryland, Stephen Tomasetti, did an experiment just a few years ago where he put scallops out in different locations. And he reported back to me that he was so upset. He called me, you know, on my cell phone at night one point and said, my experiment's ruined. He put all this effort into it. All the scallops in Flanders Bay died. I don't know what happened. I said, you know, that might not be the end of your research. Let's look into it further. And so he did. And so, you know, thankfully he had sensors out detecting exactly what was happening in the water when he had the scallops out, minute by minute. And, you know, there's a new terminology in marine science now, something called a marine heat wave. And it's not something you'd hear about on the weather. It has a very precise definition. And it has to be you're experiencing temperatures that are above 90% above the average, or the highest 10 percentile of the long-term average, I should say. And then it's sustained for several days. And so there's no doubt this happened in the midst of a marine heat wave, but also happened with what I mentioned before, this nocturnal hypoxia. The site was having the marine heat wave and going down to very low levels of oxygen at night. And just to affirm that that was the root cause, he actually did an experiment with scallops where he set up the same conditions he saw in the ecosystem setting. The high temperatures from that heat wave condition, the lower temperatures from other ecosystems, the low oxygen from that particular site, and the higher oxygen from other sites. And so as it turns out, they could handle the scallops. These top two bars are moderate temperatures, high oxygen, and then both high temperatures and high oxygen. They could handle the high temperatures on their own. But when you drop down to the lower oxygen, things got bad. And both of those conditions together were definitely led to the scallops not living very many days. So we know that oxygen and low oxygen and high temperatures are a problem. We also know that harmful algal blooms are coupled on top of this, and that we had, for example, this summer, a rust tide on the east end that started in early July, much earlier than usual, coincident with the heat wave and the rainfall that extended all the way through into September. And, you know, the problems for the scallops with regards to warming are very, very similar in many ways to what we saw with the Long Island lobster, specifically the Long Island Sound lobster fishery. This was the biggest fishery in New York State at the turn of the 20th century. It collapsed all at once, and there are no longer lobstermen in Long Island Sound. Now, the happy news is that actually marine life finds a way. Right? One of the tenets of climate change science is that animals and organisms simply move to the poles of this planet to stay in their thermal optimum. So we, as a population, we're the losers in this. Maine, however, is actually with the benefit. The lobster populations there are doing great. Now, I'm not saying the lobsters walk from here to there. What I'm saying is our population collapsed while theirs expanded. Although I will just say in the last few years, an interesting trend in Maine is that southern Maine is actually having a decline in their lobster population, and it's increasing in northern Maine. And so, you know, we may not be far out from actually the lobsters then going to Canada, but we will see. Okay, so if I didn't do enough to make everybody scared and bothered, let's turn the page a bit and point to what I'd say is probably the best example of nitrogen reductions improving ecosystem conditions, and this is in Long Island Sound. And so what you're looking at here is what the hypoxia situation looked like before the nitrogen reductions in Long Island Sound and after a 60% reduction. And so what you can see is a large swath of the sound that stopped experiencing hypoxia with the implementation of the nitrogen reductions. And just shown here, plotting the decreases in nitrogen reduction and the shrinking of that dead zone in Long Island Sound. Okay, and then, further addressing issues even closer to home here, we know that there's almost 400,000 septic systems all across Long Island. And we know there's a plan to deal with them. Although exactly how the plan gets rolled out in the future, we can discuss that further. And we have Dorian Dale here, who's been, along with the rest of Suffolk County, an incredible champion of this plan. And you can see the tagline I have in here, from worst to first. And I mean that when I say that, in that, the EPA began suing Suffolk County for wastewater practices just 6 or 7 years ago, right? Because they found out, well, what's Suffolk County doing with their wastewater? Oh, they're putting it in a hole in the ground and it's discharging to what they drink, right? What's going on with that? But I can say with confidence now that Article 19 in Suffolk County is the most scientifically based and forward-looking policy for dealing with septic systems that exists in the whole country. And I say that with confidence. I know the scientists that are dealing with this in Florida and in Rhode Island and Massachusetts and New Jersey and in Maryland. And when Suffolk County began their journey, the first thing they did was see, well, what's going on in these other states, what worked, what didn't. So it was an outward investigation. And I can say now that other states are now looking at what Suffolk County is doing as a success story. And it's not just even on the East Coast. I've literally had scientists from Hawaii come here, blown away by what they saw and looking and actually asking to meet with. And we set up meetings with Suffolk County so they could learn, how did you do this, right? Because in the same issue in Hawaii, except, the stakes being slightly different. Coral reefs are dying because they're being overgrown by seaweeds because of the discharge of sewage going. And it's even, if you think sand is permeable, you should see how fast water goes through carbonate sediments, particularly an old coral reef, just flies right through into surface waters. So the sub watersheds plan, you can see what the map looks like here. If you look at that hot pink, that should look really weird to you. That's not a linear line, right? This isn't somebody who came in and said, we'll just do this. This looks like a good area to upgrade. The plan came in and said, where should we upgrade septics to protect public drinking water supplies, right? And then it said, what water bodies are the most vulnerable to nitrogen overloading? I want you to look at the North Shore of Long Island, right? And look, there's not many hot pink areas. And this is a science-based process where they said, you know what? We could upgrade things there, but that's not a great benefit. But now look at the South Shore. Right? What's happening there? Well, what's happening there is a lot of problems. You've got a shallow water body, right? Compared to Long Island Sound, which is 100, 200 feet deep. A very shallow water body. And now this is something that doesn't get enough, it's not as intuitive, but does anybody know what the difference in tidal range is between the South Shore and the North Shore, right? You've got maybe 3 feet of tide here, and you've got 9 feet on the North Shore. And everything's being held in by that barrier island. So you've got a shallow water body, water is not moving, right? And technically they're getting about the same dose of wastewater. So you just got a huge dose relative to the volume of water. It's a huge dose of wastewater and the water is not moving, right? And that's what the sub watersheds plan did. It didn't just look at nitrogen load. It developed a whole new metric called nitrogen residence time. How long is that nitrogen sitting around to exact an effect on the ecosystem, right? And that's why you can see there's a big focus on the South Shore Estuary Reserve because of these combined factors, right? And it's not, and again, in the North Shore, there's some spots that really need it, Northport Harbor, Huntington Harbor, places like that, and closed water bodies. But by and large, again, using science to target the areas that are the most impacted. And again, a big part of it is the South Shore. And the models are run. Here's what you can decide the type of nitrogen in your drinking water that you want. And so you've got the implementation of the plan and without the plan. And, you know, anything in red, orange, or yellow is a level of nitrogen that's above 4 milligrams per liter. Yeah, and I told you in the very beginning, those epidemiological studies would tell you that's where there can be a human health effect. And certainly we know that's a level also that it can have trigger a sequence of events that we don't want in marine ecosystems. So there have been many septic systems that have been approved for use in Suffolk County. I'm also at Stony Brook. I direct the New York State Center for Clean Water Technology, where we're harnessing science to engineer clean water for the protection of public health and the environment in New York and beyond. And we've developed also a septic system here called the nitrogen reducing biofilter, nitrogen removing biofilter, that is very simple in its outlay. It's a drain field, which is used actually in most parts of the country that don't have hookups to sewage treatment plants. And underlying that is a layer of sand, and a layer of sand mixed with wood chips, that lower layer being lined to keep it anoxic to promote denitrification. There's been many systems tested in Suffolk County, and I can say that the line version of our NRB is that bar all the way on the left. So the lowest effluent of any system tested. And beyond that, we know that there's other things we don't want in our wastewater. And we've tested these systems as well, the NRBs, and then you probably can't see all the details here, but I'm showing you a list of almost 24 drugs, pharmaceuticals, industrial solvents, and other personal care products that we don't want to be drinking. They're removing up to 100%, but somewhere between 50 and 100% of these. And I can say this is better than a sewage treatment plant does. And there's no evidence of other systems doing the same thing. And certainly there's no removal in a standard system. So this is not just about nitrogen, it's also getting other contaminants out. And I could give a whole lecture as to why this is, but I'll just give the preview that sand layer with the direct injection of the fresh wastewater is one of the big reasons that these work so well. And these have been approved in Suffolk County for provisional use. We've got a couple of installers that are installing these now. Okay, but beyond dealing with wastewater, we know that groundwater travel times are decadal in many areas. It takes a long time for the groundwater to get out, and it's taking time to get systems upgraded. So we need, in parallel with dealing with the watershed issue, we need in the water solutions to protect our ecosystems right now. I'm just going to talk about a couple of those as I wrap things up here and talk about this paradigm here and something that we're all very aware of, and that is the key role that filter feeding bivalves can play in transforming an ecosystem. Without these filter feeding bivalves, you can think of it as not having a filter on your pool or in your swimming pool. Your swimming pool or your aquarium. And I always tell people to remember Finding Nemo, and we jam that rock in the filter and the water turned green. I don't know if anybody remembers that, but if you have kids, you might. Well, not having a filter is the same as not having filter feeding bivalves. Those bivalves keep the water clear, that facilitates growth of seagrasses, can prevent harmful algal blooms, and without that, you've got a system that's very prone to algal blooms. So I'm going to quickly describe a project in Shinnecock Bay called the Shinnecock Bay Restoration Program. Knowing this general paradigm, we designed this program more than a decade ago to try to see what if we brought the clams back? Could we transform the system? And we did it in a way that had never been done before, really anywhere. And I had this affirmed by a scientist in Florida earlier this year. And that, one, we weren't putting out little seed clams, right? What we've learned in the last few years is that seed clam survival is about less than 1%, right? And so unfortunately, just putting out a seed clam is great for feeding the ecosystem, but it's not great for restoration. So we purposely targeted larger clams. One, their predation, they're at their what we call the predation refuge size, so they're not going to be eaten by crabs and other predators. And two, they're reproductively active, because this whole program wasn't based on put a clam out, it's going to filter the water. It was actually based on put clams out, let them use their awesome power of reproduction to repopulate the entire estuary. we knew we actually wanted to get to 40 million new clams in Shinnecock Bay. So if you look at the graph here, we planted about 5 million. So we did not even get close, but we weren't meant to get close. We created what we call spawner sanctuaries. We put these clams very close together. Let me just see what this next slide looks like here. Okay. The idea is to put the clams very close together. Okay, movie won't run, but that's fine. In order to maximize what we call reproductive and fertilization success, right? If you don't know, clams are what we call broadcast spawners. And so how do they reproduce? They literally throw their gametes in the water. And successful fertilization is if those gametes just happen to collide, right? But if you have clam densities that are super low, one clam there, another one all the way over there, you're never going to get successful reproduction. So we literally created areas, half-acre zones, where we put in 50,000 hard clams of reproductive size and let them do what they do. And again, the idea of not to have them filter the water, but have the next generation filter the water. And so to ensure they spawn, have them grow up, and continue the work. So here's just some data on the what happened with the clams in Shinnecock Bay over time. So you can see, I mean, these bars are remarkable. And in fact, let's just see, I think, yeah. So we published a paper on this. I should have put the reference up there. It was in Frontiers in Marine Sciences last year, using the 2021 data. And so when we got the 2022 data, we said, gee, we should have waited a year, because that last bar is remarkable. And it's not just the number of clams, but what's exciting and what just proves that this whole thing is working is that the colors are based on the sizes, right? So not only are we getting more clams, but it's the proof, and it's in the size distribution. These are small clams that are being created by the clams that are already that we planted. I should also say, I think I'm gonna have a map coming up later, but beyond the production of clams, an totally unexpected outcome of this project, we were strictly focused on, let's see if we can get the clams to help this ecosystem. There was actually a whole economic part to this as well, right? Look where Shinnecock, we started this in 2012. Look where Shinnecock Bay clam landings were in 2011 and 2012, and look at their trajectory relative to every other ecosystem. And you can see now there are more clams harvested out of Shinnecock Bay than any other estuary on the South Shore, including Great South Bay, which is 10 times larger when it comes to aerial extent. And you know, the economic multipliers suggest that this has put more than $40 million into the regional economy in the area of Southampton. And based on the clams, based on the size of clams, based on their reproduction, we calculated something called the turnover time of the bay. How quickly can the clam population alone filter that water, right? And so what you can see here is how that changed over time. And essentially we went from a situation not different from what we think happened in reverse in Great South Bay. And that we think in Great South Bay, at the peak of the clams, that bay was filtered in 3 days, right? And so that kept the water quality pretty good. But we know now with the number of clams that it's probably the clam filtration may take months for them to turn over up to 3 months to turn over the bay. And by then the tides have been the dominant process. We had the reverse happen here, where by having the clams as they are, the turnover time went from being over a month to being around a week. And we think that was a big transformational point for the ecosystem, because over time, looks like some of this got skewed, but the water clarity improved. So we had more water clarity, clearer water, and decreasing levels of algae. And brown tides, we hadn't seen a severe brown tide in Shinnecock Bay since 2016. And I can say for 2017 through 2021, we had brown tides happening in Great South Bay. And we also had the recovery of nearly 500,000 square meters of seagrasses in the western part of Shinnecock Bay as well. And of course, I maybe would go without saying, like, that's the reverse pattern we're seeing elsewhere. We're losing seagrasses elsewhere. This area had a recovery. Okay, last thing to talk about are seaweeds. And seaweeds are important. They do the things we want. They are extracting nitrogen. They take up CO2. They produce oxygen. Right? And those are 3 things I've already told you are issues that we're having, and they push them in the opposite direction. And we also think they can do some things with harmful algal blooms. In the last 5 years, we've put out kelp at more than 15 locations, from as far east as Fisher's Island to as far west as the Bronx River Estuary. And 10 of these sites have been on oyster farms. We know that these kelp can remove a lot of nitrogen. If we had a 1 acre kelp farm, each year that could remove between 100 and 200 pounds of nitrogen. That's like upgrading 8 to 18 septic systems. And we know it can fight some of the symptoms of climate change. So specifically, there's Mike Dole, who I should give credit for leading a lot of these efforts in my lab. And we put out these kelp lines every year. In fact, the first site we went to was the Great Gun Oyster Farm in Richards Bay. Great oysters, by the way. If you like oysters, I recommend Great Gun. Not just because they let us do experiments on their farm. And this is in Richards Bay. And so we did an experiment where we had kelp lines and we put out oysters, juvenile oysters, either on the kelp, next to the kelp, or in a site that's far away from the kelp. And whoa, that one didn't make it.
Sorry.
No worries. If there was data here, what you'd see is that this site was actually experiencing acidification. But with the kelp, we could actually raise the pH of the water. Right? And so that, and it makes sense because it's kelp's taking up CO2. CO2 is what causes the pH to go down. So we're actually fighting back against ocean acidification with the kelp. And more importantly, the oysters grew significantly faster when they're grown in the kelp and next to the kelp compared to the control site. And with regards to harmful algal blooms, I've already talked to you about Alexandrium and why it's a public health concern. And sometimes a picture's worth 1,000 words. What you're looking there on the left is an Alexandrium cell when it's happy and filled with saxitoxin. And on the right is an Alexandrium cell when it's been exposed to kelp. And you can see it's dying off. And so what we know about kelp is that it has a lot of bioactive compounds. And it's really an amazing thing. We put out kelp lines, and where you've got the kelp along the line, there's nothing else on it. It's just the kelp. And then you go to an area in the rope that's bare, and it's colonized by other seaweeds and other organisms. So, and it only makes sense. This is, plants have been on this planet for billions of years. They can't move. They've got ways to defend themselves. So they're making bioactive compounds, and you can see in half the news, they're bioactive against these harmful algae. And you can just see here by putting out S. latissima, which is Saccharina latissima, the species of kelp, you can reduce the levels of harmful algae. I'm not going to show the data, but we've also shown that you can reduce the amount of saxitoxin that gets into shellfish if you expose it to kelp. Right? So this could be a strategy on an oyster farm, for example, because these sort of seaweeds can therefore suppress the harmful algal blooms, suppress their toxicity, increase the pH of the seawater, and rescue bivalves from ocean acidification. So I call this the halo effect because I want to be clear. We are not going to work our way out of global climate change and harmful algal blooms with seaweeds, right? That is not how we're going to do this. But we now know we can create a halo around an oyster farm, for example. And so this could be a means for protecting shellfish, giving them more oxygen, combating ocean acidification, and warding off harmful algal blooms. Okay, so I probably went on for too long, but I'm done. I've showed you how excessive nitrogen, specifically from wastewater, is a threat to ecosystems, human health, and economies on Long Island. And that climate change is accelerating. And with nitrogen, those two things together are having a compounding negative effect on coastal ecosystems and economies. We know upgrading septic systems is a primary mitigation strategy for improving water quality impairment and getting harmful contaminants out of our drinking water. And that seaweeds and shellfish, in the meanwhile, hold the promise to regionally mitigate water quality impairment and combat things like HABs and ocean acidification. So I want to acknowledge, I should have done it at the beginning, but none of this is possible. I'm just the face in front of the microphone today. And this really is the very hard work of the fine young men and women in my lab who are, I told somebody yesterday, I think in the field every day, in summer, multiple teams out making all this good work happen. So I really am so grateful for all of them, and I'm grateful to you for your attention. Thank you.
Thank you, Dr. Gobler. We really appreciate all that information and especially to see how the whole South Shore Estuary Reserve is connected. Really appreciate that. So does anybody have any questions for Dr. Gobler? Mark. You want to come up to the mic, Mark?
Yeah.
Get a little bit more slack.
Thanks. Sometimes it's hard for everybody in the back to hear the question.
Actually, I thought it was great. I'm familiar with that study that you had done, the one on the spawner.
Yes.
Sanctuaries out on the east end. And I believe you documented an 18-fold increase.
18-fold increase both in landings and in density.
Now, what I thought was great about that was obviously that was in a sewer, in an unsewered area. And if you were able to document that type of growth in an unsewered area, I was thinking, you know what? There should be no problem for you to put together a plan of utilizing spawner sanctuaries in sewer areas, which can then provide, what would you call it, a baseline, where you can say, okay, if we put in this many sanctuaries in sewer areas based on the higher water quality, we can put in this many clams. We're not going to put them in unsewered areas. We're just going to utilize sewer. We're putting in this many clams, and within 3 years, we should have this many clams. And we could actually just document it there. And I think that would make a great argument piece. If you can do that in an unsewered area, you should have a significantly better return in the sewer area, I would think.
Yeah, well, that's a great point. And I just want to, it makes me think of something that I failed to mention, that's a key component there. And that is those spawner sanctuaries, where we placed them was very, very deliberate. So before we began the project, I told you that how the fertilization occurs. And if you didn't know, I didn't say, the first 2 weeks of a clam's life is as a larvae. It's just swimming around really at the will of currents. And so that's so key in that we chose locations where we knew those larvae would then be spread to specific locations. Because what we learned is if you put a sanctuary in a particular location, 2 weeks after tidal motion, those larvae might be out in the Atlantic Ocean and they'll do no good to anyone. And so that's, that partly, anyway, that's not directed to your point, but I did want to emphasize that for everyone, that it's location for these. And I will also say that the DEC has headed up, and we've been a partner in this, something called the Long Island Shellfish Restoration Program, where this was, what we did in Shinnecock was also done in Belport Bay, South Oyster Bay, Hempstead Bay, and Huntington Harbor. The first of those to be put out was in Belport Bay. I think it was in 2019. And I don't want to make too much of it, but we're actually, the surveys of juvenile hard clams last summer were very, very encouraging. And the encouragement was in location, or the encouraging results occurred in locations where we think the Belport spawner sanctuaries, their offspring should have settled to. So it's early days, we're still working through the data, but I mean, your idea, yes, we can do this, and it's based on location, and we actually have what you're asking for. We've actually have in sewered and unsewered areas. So we're going to see now how the sewered areas, South Oyster Bay and Hempstead Bay, specifically Middle Bay, how they do relative to places like Shinnecock and Belport Bay.
Thank you, Chris. Yes, please.
Addressing kelp, you have a particular growing season that you recommend? You grow kelp all year round?
That's a great question.
And is the North Shore better than the South Shore, or vice versa, very different water bodies?
Yeah, so great question, and a nuance I didn't get to cover, but kelp is a cold water species actually. And so right next week will be spawning kelp. We make them spawn and make offspring to set up the little sporophytes that go onto kelp line that then gets deployed. So we'll deploy those probably in November. And they grow well in the fall, they slow down when it's really cold, and they grow more in the spring. But we have to pull those kelp lines out by May because they can't survive the warm water. So it's definitely a seasonal crop. I will mention, however, we're also now working with other seaweeds that are what we call summer seaweeds. So that with the ultimate goal being, we want to be combating water quality impairment during year round, but especially in summer. So we do have some red seaweeds we're working with that look very promising for putting out during summer. And yeah, location is very important. We see very vast differences in the performance of kelp in particular. We have had success both in the North Shore. That Moriches Bay site is probably maybe one of the best sites. But it's literally at low tide, it's in a foot of water, and we've grown 12 feet of kelp in that. And so we were told when we started, you can only do deep water. But we're actually finding they do great in shallow water. But the second best site is actually in Long Island Sound on the North Shore, actually particularly the Bronx River Estuary. So it needs good water movement, the right water temperature, and the right water chemistry as well.
Thank you.
You're welcome.
Do you understand the mechanism for the nocturnal hypoxia? What's happening there?
Yeah, so the question was about nocturnal hypoxia. And yeah, it's essentially during the day, when the sun is up, there's lots of photosynthesis going on, and that's pumping oxygen into the system. But when the sun sets, there's no oxygen generation. And so you get these cyclical sine waves that happen day after day, where the oxygen levels peak in the late afternoon, and then as you get to the late in the day where there's less sunlight, and at night they just go down and down and down and down, and then after the sun rises and it's finally up and illuminating the base, then it starts going up again. So it's really just a natural day-night cycle. And so what's important here is that that's in any given ecosystem. Right, so when you're in an ecosystem like on the North Shore, where we're not thinking about upgrading septics, or it's not a priority necessarily in some of the North Shore sites, you see the same cycle, but the low in oxygen is maybe 5 milligrams per liter, right? So that's not harmful. The problem is in areas where you get an overloading of nitrogen, you get an overloading of organic matter, and that's when you get down to, and frankly, I use the term nocturnal hypoxia. We actually see in many South Shore sites nocturnal anoxia. So you just get down to zero for an extended period, and that's nothing's going to be able to live there.
Wayne.
Yeah, hi, Chris. Yeah, sure. Yeah. Chris, your commentary on clams, chowder clams, I would assume. One question would be, are they available for like organizations like the Save Great South Bay to purchase? So we can experiment to them. But all the emphasis has been on oysters, that because of their cleaning prowess and the like. Are they a better bet for Saving Great South Bay, or is clams or mix, or how do you feel about the whole? Where do we go from here?
Yeah, so great questions. We got all our clams from just whole seafood distributors, and so at about 20 cents a clam. I will emphasize though, we did not go for chowders. We went for actually little necks and in that zone, and mainly because they're going to live longer. The amazing thing about hard clams is that they live decades. We think at least 40 years. And the interesting thing also is that we put out these spawner sanctuaries, and some of them over 10 years, there's been no change in density. So they're still the same densities they were when we started the program. That's not always the case. There have been issues. For example, here in Great South Bay, there was something called the channel whelk that's a predator. So you need to know the predator field as well. That's something we looked at in Shinnecock Bay. Oysters versus clams is a super interesting question and very nuanced to answer. Oysters filter more water. And so on the one hand, well, we should go with oysters. However, we did, and for Shinnecock Bay Restoration Program, we're actually doing both. Right? But we started with clams because we knew there was a baseline population to work with, where the clams we planted could be reproducing with the clams that are already there. And it's also a sign that it's a good ecosystem for clams. Oysters under natural conditions can live a very long time, but there are diseases of oysters that are age-related. And so there's a particular disease called dermal, harmless to humans, but actually can lead to the death of oysters. We don't know how long an oyster can live. We have had situations whereby after 5 years, which is a pretty long time, oysters succumb to dermal. Right now, 5 years versus 40. Well, in that case, the hard clam is a better bet. We're trying to best understand the conditions that lead to rapid infection with dermal versus the absence of it. It seems to be salinity based, but that's not a great solution because most of our bays are pretty high salinity. So anyway, I didn't give you a definitive answer, but those are some of the things that we think about. And I think are meant to be thought about going forward.
Thank you, Chris. Rich,
Yeah.
come on up.
First of all, thank you for the great lecture. With regards to the wood chip system, is that passive? And is that the only IA system that takes out PFAS and pharmaceuticals?
Great question. It's not entirely passive. It has one operating part, and that's a dosing pump. Because what we found is that the whole thing runs on bacteria, microbes in the soils. And what we found is that if you let them be at the fate of household use of water, they get flooded and then they starve, and they get flooded with household use. So we have a dosing pump where they get the wastewater is dosed about once an hour, and we find that makes all the difference. And that unfortunately fully passive doesn't work, but actually in Florida, this would be considered a passive system because there's only one dosing pump and a pump you can get at Home Depot. And you asked about the contaminants, and I don't.
Yeah, as it compares to the other approved IA systems, do they remove PFAS and pharmaceuticals?
Yeah.
Or is it only the wood chip system?
So firstly, let me emphasize, well, I threw up two dosing compounds that are removed by NRBs. PFAS are not removed by NRBs. So they do remove 1,4-dioxane, all sorts of drugs and pharmaceuticals, but not PFAS. And with regards to other systems, we don't know. They haven't been tested. But what I can say is the reason that our systems work well is that the bacteria that are degrading these compounds live in the sand layer and with lots of oxygen. And the way we have our system designed, they're getting the raw wastewater in immediately in that sand layer with lots of oxygen. And they're attached to the sand. That's a scenario that you don't find, obviously, in a traditional system. And it's not one that you find in other IA systems. So we don't know yet, but we've traced that degradation back to that. The magic is happening in that sand layer. So yeah, that's what I can say about that. And I just to emphasize, in a traditional system, there's maybe sand underneath it, but by the time you get the oxygen, much of the organic matter has been degraded, and so you don't get that removal in a standard system.
Thank you.
Dorian, did you have a question?
I actually have to exit because I have a commitment. Always great to go.
Oh, come on up.
You know, be careful with my military. I've got a big enough problem. Don't you think with the overpopulating of the area, developing, you know, I know what I see in my area. Is that a big contributing factor to this? I mean, what's the price we want to raise here? Well, I don't want to raise this development. So isn't that, in your opinion?
Yeah, I mean, you're right on. I mean, that goes back, my very first slide, what I showed you is the increasing population. And with that comes increasing use of nitrogen. And yeah, and so that's the situation we're in. And I think, you know, now it's a matter of, now that we've got this population, we're not going to roll in reverse. What are the most effective ways of dealing with that? And so, yeah.
Yes.
The really big missing part is the temperature for generally estuary, long shore, heavily armed, right? Marshes are gone, creeks are falling. Everybody wants that life. None of the research is showing that. If you look at less armed estuary and how they bore these stresses, heavily that then have something special.
Yeah, I mean, that's a great point. And obviously it's not one I've emphasized today. I have emphasized in the past, but certainly coastal salt marshes are so important for protecting, on multiple levels, right? Protecting water quality. Salt marshes can actually denitrify nitrogen. And so they can help to remove nitrogen, but if you don't have them, you don't have that service. Obviously, they're a critical habitat for both marine and terrestrial animals. And the other key thing with salt marshes is, I studied very carefully the maps of flooding after Hurricane Sandy. And I can show you the communities. One of my favorites to point out is in West Hampton. There's an area called Moneybog Bay. And then just to the right of it is another peninsula. So Moneybog Bay, there's a peninsula, there's Quantuck Bay, and then yet another peninsula. One peninsula has all the salt marshes intact. And they go on, acres and acres. The other one is fully built out, as you just described, right up to the bulkheaded edge. And you look at the flood maps, and what you see is that the communities where it was built out, everybody was flooded and further. And obviously on the other peninsula, the salt marsh actually took the brunt of the flooding. And the homes, even right next to the salt marsh, by and large, were actually protected. So yeah, it's a water quality benefit, it's a habitat benefit, and it's protecting coastal communities. So I fully agree that that's a key component in all this as well. Very good point. Thank you.
Thanks, Chris. Just one last question. I have it's a personal question that
Sure.
we found out yesterday. We got a picture from some of the oyster farmers out here in Islip showing bay scallops getting caught in their gear. Have you had any reports of the scallop population returning in the Great South Bay?
So the scallop population has been, first thing, it's super interesting about scallops. They don't even live 2 years, right? So they actually live about 18 months or so. And that's why the harvest and fall are perfect. Harvest them now because they'll be gone by next spring. Anyway, so, but as a virtue of having that life cycle, they can go through these incredible booms and busts. But, where they're talking about finding them, by the oyster farms, probably down by the islands close to the Fire Island Inlet.
Yep.
That's like a refuge of good water quality, right? It gets the flushing, and not only is it I want to emphasize, not only is it getting good flushing from the Fire Island Inlet, but as it turns out, and I've talked about this before, you never think you can predict how inlets communicate. Like when the new inlet was formed, we thought it would go to the west and it went to the east. The Fire Island Inlet exchanges great with the Jones Inlet to create a great water quality area right where those oyster farms are.
Right.
And so that's one of the few, and actually that's the area in addition that's sewered, right? And that's an area where seagrass, when they sewered that area, the seagrass actually came back to that area. So it's actually, so we've seen that before at Scouts, but it's no surprise given that great flushing, sewered, and seagrasses came back. So, and so there could be, that may be an area of hope, again, pending the temperatures not getting out of control.
Yeah, thank you. Thank you
Yeah.
so much. It is 11 o'clock, so I'm sorry, we're not gonna be able to ask any more questions from the audience right now, but perhaps Chris will stay around for a few minutes to answer any last questions. But in the interest of everybody's time, I want to thank Dr. Gobler for his amazing presentation. We're really lucky and honored to be able to take a deep dive into the science of what is happening out in the South Shore Bays. Hopefully in our work together on the report card, we'll be able to get that message out to even more people so that more programs can be targeted to areas that are in need. So thank you very much for joining us today. On behalf of the Great South Bay and our boards. What? Oh, and Leslie Hospitality, of course. We'd also like to give a shout out to Blue Point Brewing, who are making our programs possible. So thank you very much. Chris, can you hang around for a picture?
Sure, yeah. Happy to.
Thanks, great presentation.
Way to be adaptive. I'm so glad that you said like. That was great.
Oh, it's,
Thank you for helping us.
we are not doing any studies on freshwater clams. Really? All right. I want you to talk to Todd about that.